recording. Okay, well, you've learned about sequences. You've learned about sequences, and now you're going to learn about series. Okay, so, let me go down a little bit here. Let me go down here a little bit. So, an infinite series is when you add the terms of a sequence. So a sequence keeps going on and on and on, right? And if you add the terms of the sequence, you get a series. This is, how many have seen sigma notation before? How many have seen sigma notation? Okay, all right, quite a number of you have, and excellent. And here's where here's where we're going to use it. So in this context here, if you add the terms of an infinite sequence, you're going to get, and maybe I'll highlight here. Hold on. Okay, so hold on. I got too many windows open. I got to close out of a few windows here. Yeah, if you try to add terms of an infinite sequence, you'll get a sum of that form, right? You're adding the terms of the sequence. And those terms, you can represent that sum. You can write that sum, A1 plus A2 plus A3 plus and so forth, as just the series n equals 1 to infinity a sub n. Okay, and so that's sigma notation. And they mention here, does it make sense? Hold on here, let me, okay, hold on. Go this down a little bit here. Does it make sense to talk about the sum of infinitely many terms? Okay, like they say, for instance, if you were to add like the series 1 plus 2 plus 3 plus 4 plus 5 and so forth, would that series be finite? Would you get a finite answer if you added the terms of that series? 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. What's that sum going to equal of that series, that highlighted series? That's right, Renat. It's going to equal infinity, and that's not very interesting. Okay, and some people think that if you add an infinite number of numbers, that that series is going to go to infinity, but that's not the case. That's not the case. Let's take a, hold on here. Let's take a series like this. A half plus a fourth plus an eighth plus a 16th plus a 32, 1 over 32. Plus, so all the terms of the series have the form 1 over 2 to the nth power. What's happening to the terms in that series? What are the terms of the series approaching as n gets large? 0. That's right, Renat. They're approaching 0. That's right, Sophie. And so it is possible that this series might have a finite sum. It is possible. Okay, and we can actually view a series. We can view a series in terms of a sequence of what are called partial sums. So, like for instance, the first partial sum is a half. The second partial sum would be a half plus a fourth, which is 0.75. The third partial sum would be a half plus a fourth plus an eighth, which is 0.875. You see, you can look at what's called this sequence of partial sums of this series. And in fact, here in the table that you see here, they're looking at the sum. They have a table where they have the sum of the first n terms. So the first term of the series is just a half. We call that the first partial sum. So the full sum of the series is when you add all the terms of the series, the infinite terms, all those terms, right? First partial sum is the first term, that's a half. Second partial sum, when n is 2, is a half plus a fourth, that's 0.75. The third partial sum is when you add a half, a fourth, and an eighth, that's 0.875. And you keep adding these terms, and look at these partial sums. The seventh partial sum is 0.9921875. That's adding the first 7 terms of that series. What do these partial sums seem to be approaching? What are those sums? Those sums, they seem to be approaching 1. That's right, Renata. And in fact, if the sequence of partial sums approaches a value, that means then the series it converges and it approaches that finite value. So in fact, it turns out that this infinite series equals 1. It equals 1. Absolutely amazing. Even though you keep adding terms, as you know, the series goes on, and you keep adding more and more positive terms. The terms are the rate at which they approach 0 is fast enough so that the infinite sum equals 1. Okay, and that's the idea. That's the idea behind a convergence of a infinite series. They formalize it more. They formalize it more here in this definition. Okay, so in the definition, you can denote the nth part. You have an infinite series, and you denote the nth partial sum as the sum of S sub n. S sub n is the sum of the first n terms. We say the sequence of partial sums is convergent, and the limit of the limit of the partial sums as n goes to infinity equals the sum. If that's the case, the sum S, then the series converges, and the sum of that series equals S. So just like a sequence, an infinite series can converge or it can diverge. For the series to converge, the infinite series has to equal a finite sum. Okay, so are there any questions on that? All right, well, let's go ahead and look at a very special series here called a geometric series. And what I want to do is I want to go right to an example. I want to go right to an example here. Okay, let me give you a moment to copy this example down. Okay, so this is what's called a geometric series. Now, a geometric series is a series that can be written in this form. Okay, let me actually go to the whiteboard here. Okay, so a geometric series is any series that can be written in this form. That's called a geometric series. Okay, and R is what's called common ratio. Common ratio. And it can be shown that if the absolute value of R is less than 1, the series, the geometric series, converges. If the absolute value of R is greater than 1, the geometric series will diverge. Okay, they prove this in the book. It's not hard to prove. In example 1, they prove it. So let's look at this sum. We'll go back to the problem at hand, but let's look at this sum. So the sum that we have, right, is 1 plus a third plus a ninth plus a 27th and so forth. Okay, now we could write this sum, like this. One moment. We could write that sum as a geometric series with a common ratio of R, and the first term is A, which is 1. So 1, the first term of the series is your A. Now, what's this common ratio mean? Well, if you take the second term of the series and divide it by the first term of the series, that's 1/3 over 1, which is a third. If you take the third term of the series and divide it by the second term of the series, that's a ninth divided by a third. That also equals 1/3. Hold on. So in other words, with a geometric series, you have a geometric series if you have a common ratio. And that means that the n plus first term divided by the previous term, the nth term, will equal that common ratio. And that's in fact the truth. Another way of thinking about it is if you take 1 times a third, you'll get a third. If you take a third times a third, you'll get a ninth. If you take a ninth times a third, you'll get 1/27th, and so forth. So this is a geometric series, and the geometric series, will it converge? Well, the common ratio is a third. Is the absolute value of 1/3 less than 1? It is. We have to do the absolute value of a common ratio. That's right, Renaud, because sometimes the common ratio can be negative number. So in this problem we were looking at, we can find the sum of the geometric series. We can find it. And, all right, the question is, what is that sum? It's a convergent geometric series. Okay, let me give you a moment to, copy up to here. And then we'll talk about the sum. I mean, we have a convergent geometric series. This means the series has a finite sum. Let's see if we can figure out what that sum is. There's a formula for it. There's a formula for it.
Professor, I still don't quite understand how a geometric series is different than a regular series. Could you elaborate on that one more time? And why is it called a geometric series also?
Well, the one moment.
Okay.
Okay, I was going on Google real quick to try to, why is a geometric series called a geometric series? It has to do with what's called a geometric progression. If you look at the terms, like you start at 1, and then a third, and a ninth, and a 27th. So if you take, the common ratio, if you take the second term of the series and divide by the first term of the series, you get a third. If you take the third term of the series and divide by the second term of the series, you'll get a third. It's called a common ratio. Anytime you take, and then etc.
Okay, so dividing the one term by the one prior gives you the same ratio.
That's correct. Common ratio.
Okay.
That's right. And this is going to then give what's called a geometric progression of terms. And the thing is, you see, there's a formula in the book that says if you have a convergent geometric series, the sum of that geometric series is going to equal A divided by 1 minus R.
That ratio, the common ratio. Okay.
And so the first term of the series is 1, common ratio is a third, we'll get 3/2. So for good questions. For geometric series, if the geometric series converges, you can find its sum.
Alrighty, thank you.
All right, you're welcome. Let me go to another example. This one I'll actually go to in the book here. Are there any other good questions on this one? I want to make sure you have enough time to copy it. Let me know when you're done copying, and then I'll move on. Okay, Maria's good. Thank you, Maria. All right. So let me go in the book here, in the ebook. Let me just yeah, we got it here. Hold on. Okay, so hold on here. This is the formula in the book. A geometric series is convergent if the absolute value of its common ratio is less than 1, and its sum is equal to the first term, a, divided by 1 minus the common ratio. So for example, if we look at the second example here, you know, you know, they're saying exactly what I'm saying, right? Right there. So here in example 2, let me just hold on. I just want to take a little bit of this off here. So they want you to find the sum of this geometric series. 5 minus 10 thirds plus 29ths minus 40 27ths plus, and so forth. So if this is a geometric series, there must be a common ratio. Well, it turns out that the common ratio is r equals negative 2/3. Okay. If you take like, I mean, you could take negative 10/3 and divide it by 5, and you'll get negative 2/3. You can take 29ths, the third term of the series, and divide by the second term, negative 10/3, and get negative 2/3. But sometimes it's easier to do this. 5 times what fraction equals negative 10/3? 5 times negative 2/3 equals negative 10/3. So if you take the first term of the series, 5, and multiply it by negative 2/3, you get the second term of the series, which is negative 10/3. Now, if you take the second term of the series, negative 10/3, and multiply it by negative 2/3, the common ratio, you get 29ths, the third term of the series. If you take the third term of the series and multiply it by the common ratio, negative 2/3, you'll get negative 40 27ths, which is the fourth term of the series. So that's another way to think about the common ratio as well, and a way to, for me personally, it helps me feel good that it's a geometric series doing it that way. How many kind of like looking at it like that? Okay, Jacob does. And all right, well, now what's the sum of this? The absolute value of negative 2/3 is 2/3, which is less than 1. So the series converges, and the sum is going to equal a divided by 1 minus r, which is going to be 3. So if you were to program this series in a computer and have it add up, have it like for the rest of the time, add up the terms of the series, it just, series keeps going and going. The sum of those terms would equal 3. Okay, are there any questions on that? Okay, let's look at another example. If the absolute value of r is greater than 1, then the series diverges, and it just never converges to a finite value. Here in the, hold on here. Maybe I can unhighlight. Hold on. In the little theorem here, theorem 4, see? If the absolute value of R greater than or equal to 1, the geometric series is divergent. And that means that the series, it just doesn't have a finite sum. It just doesn't settle down to a finite sum. Divergent series are not very interesting to us. It's the convergent series that are interesting. Good question, Marcus. Good question. You're good, Marcus? All right, excellent, excellent. Okay, well now let's look at another series here. Okay, here's a series, and we want to know if the series converges or diverges. Let me give you a moment to copy that down. Okay, so let's see here. This series, so this is not a geometric series, right? It's not a geometric series. What would like what would the first, if we were to like write some terms down of this series, what would the first term be? Like when n equals 1. What's the first term of the series equal to? That's right, 0. Okay. What's the second term when n equals 2? What's that term going to be? 1/9. That's right, Renaud. Now, please stop me if you're uncomfortable. All I'm doing is I'm substituting 2 into the term here, right? Okay. Now, go ahead. Take a moment to write down the next 2 terms of the series. And then I'll write them down, and you can tell me if they're the same as what you got. Here. Okay, 2/14 and 3/19. Who got those as the next terms? Okay, good, Sophie. Let me see here. Some other folks too. Good, Renaud. Good, Marcus. Michelle, good. Good, Jacob. Okay. Sophie, I don't know about series in terms of Desmos. I'm not sure about that. Uh, I'm not sure. Um, to be honest, I want you to use your intuition a little bit without technology right now. Maybe in the future we can investigate that, but I kind of doubt it. I mean, I want to be careful. I'm not sure right now about a series in terms of Desmos, but we could, maybe in the future look at that. But I want you to, all right, good. So is this a geometric series class? Is this a geometric series? No, no way. Not a geometric series. Do you think this series converges or diverges? What do you think the terms, if you think about the terms of this series, okay, you got n minus 1 over 5n minus 1. Now, what happens to the terms of that series when n is large? What are those terms of those series, the terms of the series, start approaching when n is very large? Do the negative 1, well, what I'm trying to say, okay, I'm getting some good okay, that good responses. Now, Leping says 1/5. So let me ask you, when n is large, do these ones matter in terms of like the terms of the series? Do they matter much in terms of, no, they don't. So really, when n is large, the terms of the series start behaving like n over 5n. And n over 5n is 1/5, right? So this series here, the series is going to diverge. It's actually going to diverge. And some of you, when you chatted it out, like Maria and Renat, I mean, your instincts are telling you the series is going to equal infinity, and you're right, because if you look at how the terms behave, okay, when n gets large, the terms are going to approach 1/5, and 1/5 is not equal to 0. In other words, the terms are not getting smaller. The terms have to approach 0 to have a chance for the series to converge. Now you're going to learn actually that it's not enough for the terms just to get smaller for the series to converge. But for the series to have a chance to converge, the terms of the series have to approach 0. They have to get smaller for the series to have a chance of converging. So this series diverges by the test for divergence. Okay. Now let me just show you what that test for divergence is real quick. Hold on here. Let me find it here. Yeah. Let me just go. I'll go back to the problem, but let me just get this out of the ebook. Okay, the test for divergence says that if the terms of the series, the limit or the limit of the sequence of terms of the series does not exist, or the limit of the sequence of terms doesn't equal 0, then the series has to diverge. That's called the test for divergence. Okay, that's called the test for divergence. Okay, so if we go back to the problem here, hold on here, let me get it back here now. Okay, so here was our series. The terms of the series approach the terms of our series approach a fifth. So therefore, the series diverges by the test for divergence. Another way to think of it is like this, intuitively. If you were to write out, write out some terms of the series, okay, and kind of go into the tail of the series. Well, not the series doesn't really have a tail, but like for instance, if so like here I have the first term of the series, second term of the series, third term of the series, fourth term of the series, and the series keeps going. And now here, this 4,999 over 2,499, what term is that in the series? What term is that? In other words, what I'm saying is this term here is A sub what? A sub, what term in the series is that? That's right, good, A sub 5,000. And then the next term in the series, this term here, would be A sub 5001. Right, and those terms, they're starting, if you compute those terms on your calculator, okay, if you compute those terms on your calculator, 4,999 divided by 24,999 is 0.19967, okay, which is pretty close to 0.2. So essentially what's happening is eventually the series, how's it going to behave? The terms of the series are going to basically be as you go out into the series, as n gets large, the terms of the series are going to be, basically be equal to 1/5. So it's like you'd be adding 1/5 infinitely many times, and so you're going to get infinity, and therefore that series diverges. Okay, is this, how many find this helpful? This extra little set of comments that I have. Is that helping you get a feel for this? Okay, Sophie likes it. Good, good. Leping likes it. Wonderful, wonderful. Well, this is we're going to talk more about series next Tuesday, section 8.2. But you at least have some fundamentals. And are there any questions on this problem? Okay, well, on that note, I'll stop the recording.